Okay, my dear students, welcome. Now continuing with our previous discussion on calculus of residues. As I told you, this calculus is so useful in calculating complicated integrals, and that is the main objective of this topic, the complex functions of complex variables. You know that the entire target for this course on mathematical physics is to make ourselves quite capable to solve integrations and to solve the differential equations. Okay, now in my last lecture I introduced the residue theorem, which is such a useful theorem, and in the previous lecture on chapter 7 I introduced the singular points of a given function. There are two types of singular points. One is the pole of certain order and the other is the branch points. Okay, now today applying the residue theorem to solve certain integrals. Okay, now that is our today's presentation. Let me go to my notes and you can also see. Okay, so this is the first application, evaluation of definite integrals of the functions which are functions of sine theta, cos theta, etc. Now this is the example 7.2.1, which you will only understand if I tell you about the how to calculate various types of integrals. Now let me go to my notes. These are the notes on chapter 7, and let me jump to I also discussed these methods to calculate poles. Now let me, okay, so that is the page which I wanted to display. So here is an integral of the type of functions of sine theta and cosine theta. If you happen to see the integrations of such functions and you want to solve them using calculus of residues, so first of all we have to convert the given function, which is a function of real variables, and the integral is also a definite integral. So we will convert this function into a function of complex variables. So we will introduce z, and we will put z is equal to e to the power I theta. So we are going from real line to complex plane, and then dz is equal to I e I theta d theta. So that d theta is equal to this. Sine theta, you know, is z minus z inverse over 2i. Cos theta is z plus z inverse over 2, and when we substitute these values in our function becomes, this is the function of sine theta and cosine theta, and here is dz. So we will calculate this integral now using calculus of residues, and then we will apply the residue theorem. Okay, now let me discuss an example on this issue. Rather, we will solve one of the exercises. Let me find this exercise. Where is this solved exercise? Okay, so here is this exercise 7.2.4. You may have a different number in your version of the book, but the problem is to find this integral from 0 to 2 pi of d theta over 1 plus epsilon cos theta. So we have seen that this integrand is a function of sine and cosine theta here. So we will immediately introduce z equal to ei theta, which is a unit circle. Dz is equal to this and cos theta is equal to this. So as we substitute this here, we get this integral. So this definite integral from 0 to 2 pi is in fact the contour integration over a closed path, and we have substituted these respective values here. So we have converted our integral from the integral of the real variables to the integral of complex variables, which is equal to this. It means we can now apply residue theorem. Okay, so first of all we have to detect where are the singular points of this integrand and what are the poles of these on these singular points. So the poles of this integrand are obtained by solving this quadratic equation, and we get two values of z, -1 plus 1 minus epsilon square under root, and -1 minus 1 minus epsilon square under root. So when epsilon is between -1 to +1. Okay, now we see that this pole z1 with -1 plus into 1 minus epsilon square over epsilon square, this pole lies within the C. What is C? As I told you, the contour we have taken as the unit circle. So obviously this is the only singular point which lies within C, and the other pole, which is Z2, goes outside this C. So we will be interested to find the pole of the function at this value of singularity, and this is what I have done here using one of the techniques to find the residue, and the residue at this value of z1 comes out to be this. So as soon as we calculate the residue of the singular points included in the pole, we immediately apply the residue theorem, which is equal to 2 pi I into residue, sum of residues. There is only one residue, and we get the value of the integral very easily. So this was the first type of functions which we are able to calculate integrals, which are we able to calculate these integrals using calculus of residues. And this is also briefly shown here in this example 7.2.1, and you can go through this example and make your experience. Okay, the second type of integrals we are interested to solve the calculus of residues is the definite integrals of this type. So here we have a certain function with certain restrictions, which we will describe here. These are the two restrictions, that f of z is analytic in the upper half plane except for a finite number of poles. It will be assumed that there are no poles on the real axis. If poles are present on the real axis, then that may be included or excluded as discussed earlier in this section. And this is the second requirement, that f of z should vanish strongly as 1 over z square when the argument lies between 0 and pi. So with these two restrictions on this function fx, we are now able to find to calculate these integrals using calculus of residues. Now the technique is explained over here, here we will take the contour of integration as shown over here, that is minus r to plus r, and then going over a semicircle and coming back to minus r. So this will be our contour of integration, and to convert this integral into an integral of complex variable, we will simply substitute wherever is x, we will substitute z there, and that will give us. So if we briefly go to the formalism here, so f of z is equal to limit from minus r to plus r, this is this leg of the contour, and then going over the semicircle with r tending to 0 from 0 to pi. That is, we will take the semicircle as large as possible, and this will make this term equal to 0, because when we go with z tending to infinity, we have the requirement that our function tends to 0. So we are left only with this, and this is how we will apply the calculus of residues and to get the value of the integral. And this is an example on this technique, example 7.2.1. so go through this example along with the detail given in my notes. You will require that detail definitely, so to discuss this example and to see that the value of the integrals comes out to be pi. So in this case also we converted our integral from the integral of real variables to the integral of complex variables, and then we were able to use calculus of residue or residue theorem. Okay, so that's it for the second type of integrals. Now we extend this type to the type 3. So this is the type 3 of integral, that f of x along with this component e to the power I a x. So this integral is more complicated, but we will see we will have the same requirement for fz as we had in the previous case, and we will now prove that we can also solve this integral using the same semicircle as the contour of integration and the same thing, but we will have to prove that the new integrand fx along with e to the power iax, this will be fz into e to the power iaz, and we will prove that if fz tends to 0, then this total integrand also tends to 0. So this is shown here, this is proved here. You will have to go through these pages and with the help of my notes. So once we prove that this total integrand tends to 0 as fz tends to 0, now this is the statement of the Jordan's lemma. It is given somewhere here. Okay, let me show it from my notes. I think I have stated this on a separate topic. Okay, this is Jordan's lemma. Here is the proof, and the same thing, but you will find more detail here to give. This is Jordan's lemma. You will find the statement of Jordan's lemma and the proof of the Jordan lemma given above. So it means then we can use this technique of calculus of residues even to cover this third type of integral. Okay, now let me go to the next example, example 7.2.3. In this case, in the previous case, we had the requirement that f of z, there should be no pole on the contour of integration, that is on uh, this is the contour of integration, so there should be no singular point on this path. But if there is a singular point on this path, as is the case in this example over here, because this, when we will convert this into this integral as the integral of the real variables to the integral of complex variable, we immediately see that z is equal to 0 is the singular point, and z is equal to 0 exactly lies on the contour of integration. So if you happen to have this situation, then the only thing we can do is that we can start from this point, go as close to the origin as possible, and then we can divert ourselves over another semicircle, upward or downward, and then go back to this. So if we go upward, it means we are excluding this singular point, and if we are going downward, it means we are including this singular point, and then we will use the calculus of residues to solve this integral. And this integral is solved in detail in my notes, and here is the detail. So you can see this detail and use this technique. So what we have done so far in this chapter, we have introduced the singular points, we have discussed the types of singular points, we have also derived the residue theorem, and we have now, as application of the residue theorem, evaluated 3 or 4 types of integrals, and that has made our life easy. So we are now able to solve such integrals, and this was the main purpose of this lecture. Right, so that's all about my today's lecture, and also we have finished with the theory. However, in my next lecture we will discuss the problems. Okay, thank you very much.